All right, welcome to another day. It's another day, another problem, eh? Restore IP addresses. So it's a LeetCode medium, in my opinion, based on how convoluted the solution seems and unintuitive, counterintuitive. I say this is a hard problem, but they say it's simple. Not simple. They say it's a medium. But let's get to it. We're still evaluating the backtracking pattern, where you do typically involves recursion and eliminating wrong solutions that don't work for what it is you're working on. So let's look at the problem without any more delay. Given that a string S contains digits, return a list of all possible valid IP addresses that can be obtained from the string. The order in which IP addresses are placed in the list is not important. Now, a valid IP address is made up of 4 numbers separated by dots. For example, 255 dot yada yada yada. Each number falls between 0 and 255, including 0 and 255, and none of them can have leading zeros. So out of this, we get these numbers, right? Just as an example. From this, we get these 2 valid IP addresses. From this one, we get this 1 valid IP address. From this, we get all these valid IP addresses. I'm of the opinion if someone asks you this question in an interview, they're out to get you. And because for one, the naive solution is way more intuitive than this backtracking thing. And in a code base that is not maybe a one-off thing, that maybe it would be worth, well, it depends on the context, really. I mean, if you're building for the world, right, your code is running on so many devices, then you're probably doing a significant amount of causing a significant amount of greenhouse gas emissions by simply not using the optimized approach. But I mean, if it's a small project, you have like 5 users, bruh, just go naive for real. Like, it's really not worth the stress, and you're gonna see what I mean shortly. So they restate the problem, and in a naive approach, I think it's worth reading out, because it's very little. Now, the naive approach would be to check all possible positions of the dots. And to place these dots, we initially have 11 places, then 10 places for the second dot, 9 for the third dot, and so on. And then it's made up of 4 numbers, basically. So you don't have more than 3 dots. You never have more than 3 dots. So that means in the worst case, you need to perform 999 validations, which is 11 times 10 times 9. And it's like a tree structure. So you have, in the worst case, you have 12 numbers, right? And you have to put 3 dots in between them. So in the worst case, for placing the first dot in the 12 numbers, you have 11 places in between those 12 numbers, where you can put that first dot. Now, for each of those 11, each of them have 10. There are 10 places where you can put the second dot. And so on. And then for the last dot, the third dot, right, you have 9 other places where you can put the last dot. So that's where they get this computation. And now, after placing the dots, each resulting, so just think of it like a tree structure, this explanation like a tree structure. And I think if you can visualize that then internally, then that would help a bit. But now, after we place these dots, each resulting substring between dots must be validated as a valid number between 0 and 255 and must not have a leading 0. So a 0, no, you can't have 0, 1, right? Overall, this approach has a time complexity of O of n cubed, and I want to comment on this a bit. Due to the 3 nested loops required to place the dots, the space complexity is O of 1 because we're not storing any additional data structures. Now, this O of n cubed, we know exactly what n is in this case, because I mean there's a highest number, right? N cubed, whatever it is not going to exceed this, right? So technically speaking, this is a constant time problem. Yeah, not really n cubed, if we're being honest. It's because we know what n is, right? Sure, it's a loop within a loop within a loop, but based on the data constraints, right, how we're bound from 0 to 255, etc., and 4 numbers from 0 to 255, we know the upper limit. So this is actually O of 1. Even the naive approach is O of 1. The solutions, the problem space doesn't grow asymptotically. It's cut off, right, at this value. So you can call it O of 1. We know exactly what that is. Now, so that's all well and good. And I don't know if now is a good time to show this naive approach. Actually, now is as good a time as any to do that. So give me a second. So this is what that solution looks like. So we are checking, we have some utility functions here, and I can step through them. Basically, we want to check if there's a leading zero. So if the first character in the string is 0, right, and the string is not 0, so 0 is valid, but if the first character is 0, then we have a problem. Okay. Now, how do we check if it's valid? If there's no leading 0, and whatever the value is, so we convert it from a string to an integer. That's what this does in JavaScript. We check, oh, is it less than less than or equal to 255? Then it's valid. That's going to return true, right? This expression is going to evaluate it true. And now a valid IP address is one where this is interesting, and it ties into this. But basically, we're going to have an array of the different chunks that we construct over here, right? And every single one of those needs to be valid for that particular IP address to be valid. And that's what this function is checking. So you can see the loop within the loop within the loop here. We have I, j, k, I initialized at 1, j at I plus 1, k at j plus 1, everything less than length. So far as less than length, keep going. And then we construct this IP address this way. We use slice operations. It's 4 numbers, right? IP addresses are made of 4 numbers. We put them in this array. That is what's being checked here, right? As you can see. Right, before we now end up joining them if they're valid. If this returns true, we return them valid. Boom, problem solved. You're done. Easy. Oh, brother. But unfortunately, we don't like taking things easy, right? We like stressing ourselves, squeezing that last ounce of performance from the problem. So let's start to suffer with the optimized approach using backtracking. So to optimize for the worst case scenario mentioned in the naive approach, we'll use backtracking along with constraint checking. Okay, so what is the constraint we're checking? Now the idea behind this concept is that once we place a dot, we only have 3 possible positions for the next dot. After 1 digit, after 2 digits, and after 3 digits. Okay. Now this constraint helps us reduce the number of combinations we need to consider. So instead of evaluating, okay, you placed, let's say you had 12 characters and you placed it at the first number, and then having to evaluate every single space from character 2 to 11. In this case, we're saying, oh, actually, when you place the first dot, your next dot is not everything from 2 to 11. It's actually everything from 2 to 4. So you can only place it after 2, after 3, or after 4, because you cannot have a number that's longer, that has way more digits than that. So your solution space is cut down significantly. We only have to check actually 27 combinations. How about that? 27 combinations. Instead of checking every single combination, right? With the brute force approach, naive / brute force approach. And so now instead of every child having 11 nodes, then each of those nodes having 10 children, then each of those 10 children having 9 children, 9 possibilities to construct the IP addresses, a lot of which are invalid, right? Because, for instance, if you put your dots, let's say you have 12 numbers, and you put your dots after the first, after the second, and after the third, that last digit must be incorrect, right? So there was no point in constructing that. So in this way, we are invalidating, we're checking fewer things, basically. We're cutting off every combination where a number has way too many digits. So we've cut the solution space significantly just by doing that. And now we're going to use backtracking to implement the algorithm where we only have to check 27 combinations in the worst case. And now we'll implement the backtrack function. It takes the position of the previously placed dot, previous dot. And I think I'm going to move between this and the code. So they say here, it's going to take a function that takes the position of the previously placed dot, so the parent dot, and the number of dots to place as arguments. Okay, so this is our backtrack function. It takes the where the dot was previously, its position in the number, and the number of dots we have left to place. Now we're going to iterate over the 3 available slots with this current dot cursor to place a dot. And now what does that look like? It looks like this. So we're going to iterate we set current dots to the space after the previous dot, now we have this max position thing. So a max position represents either the position at the end, the last character in the whole string. So that's what size minus 1, because we got the size here, or previous dot plus 4, because you remember we only have 3 spots that will be valid for the next point anyway. So that's what that is. Okay, so check if the current segment from the previous dot to the current one is valid, and that's what this is, the segment from the previous dot to the current dot, if it's valid. So we're checking if that is valid, and it's a similar valid function to what I just showed, although everything is in one pass, so it's a bit more complex, and you can check that out later in the code base, because this is not very important. It's not like a core part of understanding the solution for now. So we check if that's valid, and if it is valid, we place a dot by adding that particular segment to this list of segments that we have that currently is an empty array, because when we call the function in the beginning, you can ignore this. We start off with an empty array for segments, empty array for results, passing in a string. Previous dot start from -1 because we haven't started yet. There's no previous dot. Basically, we have 3 dots to put, and we're constructing the solution. Super complex, super duper complex, and this video is going to be too long if I start stepping through with the debugger, so I recommend you do that in your spare time. And there are already some cases for you to try out, particularly this case. Look out for this case. It's going to help you maybe see where the backtracking is happening. But even then, following debugging a recursive function is hard in general. That's why, I mean, I learned NASA they don't use recursion. They just always follow an iterative solution instead of a recursive one, regardless of how elegant the recursive one looks. And now, so we push that dot, and then when we're done pushing dots, basically, so if we've put all 3 dots, but in this case, assuming we're just getting started, we haven't put all the dots, we've only put 1 dot. So if we're evaluating this number, for example, and this input IP address, we put the first dot is going to go here after 2, basically. So that's what this does. That's what this means. And we push that segment in there because 2 is a valid IP, part of an IP address. So it's going to put it in there into this array, right? It's getting constructed. The segments array is getting constructed. And now the dots we're not done yet. So we call backtrack again, but with the same string, this same big, huge string over here. Make it bigger, 255 over here. And a previous dot. Now, the previous dot, we're going to set it to current dot, because current dot, we set current dot to, where's current dot? Yes, we initialize it to whatever previous dot was before plus 1. So in this case, previous dot is 0, right? Yes, previous dot is now going to be 0, and we've just used 1 dot because we just put 1 after 2 in theory, right? Ignore this. We assume that we are still just evaluating 2 for now, and and we pass in all the segments. So far, we only have 2 in it, and we pass in the result, which we haven't done anything with yet. And now we're going to do the substring again. So previous dot was at 0, now it's going to be 1. Current dot is equal to previous dot plus 1. So 1 plus 1 is 2. And when you do substring, it's going to pick the next thing. So basically, it's going to pick 5, essentially. So that's how all of this gets populated, this segments array with 2, 5, 5. And then at the end, right? At the very last one, when we were out of dots, we're calling it over and over again about decrementing dots each time. When we're finally out of dots, yeah, we're going to call update segment. So when there was 1 dot left to place, basically, so 1 minus 1 is 0. When there was 1 dot left to place in this backtrack function, after calling it recursively, we get to this last stage here, where we have this string, our whole string. We have the current dot, which is going to be started off at 0, 1, 2, right? And we have 3 dots to use. We have our segments that we've constructed so far. In this case, it would be 2, 5, 5. We haven't done this one yet. Then we go to this update segment function. And now is where some last checks, final checks happen. So we get based on current dot plus one to the end of the string length, because it's the last one we're evaluating. We get that segment, and that's going to look like this, basically. Now, if that is valid, in this case it's not, because it's highlighted in red, it's not valid. But if it were valid, we would add it to the segments, join the IP, and push it in. But now it is invalid, right? It doesn't work. So what do we need to do? We don't do anything. We just know, okay, we don't need to update the segment. Instead, we need to backtrack, right? Because we've hit a dead end. And there were different ways to hit a dead end. Either you hit a valid solution where update segment would have triggered, or you don't, and then that doesn't happen, right? That doesn't trigger. Either way, this is the backtracking step. We remove the last place dot. So we're going to remove that dot that we put here. The dot that we put that led to this, basically, because this has to be revisited. We have to go to a parent of the steps that we're evaluating. And what's going to happen when we do that? The current dot is gonna be incremented, because we're still in this for loop technically. We just went into a recursive detour, and now so we've popped one off the stack, and then current dot is gonna increment. It's gonna move forward again and lead to the current segment, right? Another segment being 52, right? So it's gone one level up, and it's gonna check, oh yes, this is a valid segment. It's gonna put it in there. So that's how we end up having 52 here. And now afterwards, we call backtrack again and come to this point where actually no, we come to this point at that point actually, and we evaluate once again this last section. So it's building the solution from the end actually and cascading it up to the beginning. And when we do that, it's going to be invalid, so it's going to pop again. So that's going to get popped, and then this one is going to be the next thing that's going to be evaluated here. Like when current dot is going to be moved again to evaluate that case. Oh no, this video is 11 minutes, 17 minutes long. Well, I'll try and wrap it up by the 20th minute. And so we now see that, oh, actually, this is invalid. This segment is invalid, right? From here, this segment up at this point now, not even in the update segment section, but in this section is actually invalid now. And so what do? We just get rid of that invalid thing, right? Remove that invalid thing from there, right? And then evaluate this instead, right? So backtrack again to the top. So to that particular for current that is going to be able to, where previous was right after 2 and current is like right after, it's 2 steps after, and check that. So that's good, that checks out. Then this as well, we go to the next one, it checks out as well, but this still doesn't check out. So we just keep trying that over and over again until we get something that checks out. And in this particular example, you have to keep going until this is valid, right? And every other thing in it is valid. And that will require you getting up to 255. How about that? Before things start to look like they're getting there, basically, where the positions are. And there's only one correct answer. So yeah, terrible. Wasn't the brute force solution way better? Yo. So that's all for this problem, honestly. Let's look at the time complexity. It's O of 1, right? Because we only have to check 27 combinations. Like I said, the other one too is O of 1, because we know exactly what n was when they said n cubed, even though it was a loop within a loop within a loop. There's an upper ceiling that is a finite number that is relatively small in computing terms, right? 1,000, having to check 1,000 things is no big deal. To find 27, anywhere from something less than 27, right? Like 27 items, correct items, possibly correct items. And so the space complexity is constant, since we can have 19 valid IP addresses at most. So we have at most 19 valid IP addresses for any given combination. And the relationship, hold up, this is scrolling. Okay, so the relationship between the length of the input string and all possible IP addresses that can be generated from the input string can be visualized in the graph below. So the maximum from a string of length 8 is 19. Anything less than 8 will have fewer valid address combinations. Anything bigger will have fewer. So yeah, when you have 12 numbers, if your string length is 12, there's only one possible IP address at that string length, it seems. One possible valid IP address. So yeah, you have that. Super complex, should be a hard problem in my opinion, but I've gone on for long enough. See you in the next one. Goodbye.